Hey folks, Professor Gray here, ready to talk to you about discrete probability distributions from probability and statistics. But first, let's do a little bit of an inequality review. We'll translate these inequalities from words to mathematical symbols. So here in number 1, x is at least 12. If we were to notate that mathematically, we would denote it as x can be 12 and it can be anything bigger. So x is greater than or equal to 12. For number 2, x is at most 3. Well, that implies that x can be 3 or anything less than that. Number 3, x is no more than 6. X can be 6, but it can't be more, so it'd have to be less. Number 4, x is no less than 10, so x can be 10, but it can't be less, so it would have to be greater than. Number 5, x is 54 or fewer, so x can be equal to 54 or anything less. And number 6, x is, so it can be 38 or more, which is greater. The ability to translate these from words to symbols will be very useful in this and subsequent chapters. Speaking of chapters, earlier in this course you talk about representation of data, such as distributions. And we also talked about probability, the fundamentals of probability. Things like the complement rule, the addition rule, and multiplication rule. Well, and then this chapter and in the next chapter, we'll combine these and explore probability distributions. And part of what's motivating all of this is the rare event rule for inferential statistics, which is used later on in hypothesis testing. It says if under a given assumption the probability of an observed event is extremely small, then the assumption is probably not correct, and the event is called statistically significant. Well, in order to be able to say if something is rare, the probability is rare or extremely small, we've got to be able to calculate probability. And that's part of why we're talking about probability in probability and statistics. And that's part of why we're talking about discrete probability distributions today. First, a term. Random variable is a variable, typically an x, has a single numerical value determined by chance or at random for each value or each outcome of a procedure. So a random variable is a variable whose value is determined at random, as the name implies. Also, to review the difference between discrete and continuous variables. Discrete variables take on individually separate and distinct values, and they're finite or they're countably infinite. For example, a number of times your dog bit the mailman last week, there's a discrete number, either 4 or 5, not 4.5678942. Continuous variables, on the other hand, can take on an infinite number of values along a scale. They are uncountably infinite in their nature. So the heights of women in New Jersey, for example, there are an infinite number of possibilities along a range. For those, they are continuous data values. Well, all probability distributions, whether they're discrete or continuous, have 3 characteristics. Probability distribution is a description that gives the probability for each value of the random variable, and here are the requirements. The numerical values of a random variable are associated with corresponding probabilities. The sum of all those probabilities is 1, and each probability must be between 0 and 1 inclusively. So it can be 0, it can be 1, but it can't be less than 0 or less than 1. Or excuse me, more than 1. Well, let's take a look at these and see if they are probability distributions. Number 7 is the number of 4 children with a certain genetic disorder. Alright, so I've got numerical values of x, and they correspond to probabilities. That's good. If I add up all those probabilities, I get 1 or 100%. So that requirement's met. And none of these probabilities are below 0 or above 1. So yes, number 7 is a probability distribution. Number 8, most fun way to flirt. That is not a probability distribution. Can you see why? Well, the first requirement is that I have numerical values of x corresponding to probabilities. Email, in-person, instant message, and text. All of those are not numerical. So this is not a probability distribution. And what about number 9? Number 9, when to discuss salary. X is the number of interviews, so numerical values of x correspond to probabilities. That's clear. All the probabilities are between 0 and 1 inclusively. However, if I add the probabilities, I do not get 1 or 100%. It falls short of that. So number 9 is not a probability distribution. So again, 7 is, 8 and 9 are not. Here are a couple of other examples. These are written in a different way. Number 10 is given as a formula. P of x is x over 6, where x can be 0, 1, 2, or 3. Well, x is numerical, 0, 1, 2, or 3. And if I substitute a value of x into the formula, I do get a probability, so that part's good. And all of the probabilities are between 0 and 1 inclusively. So 0, 6 would be 0, 1 sixth, 2 sixths or 1/3, and 3 sixths, that's 1/2. If I add up these probabilities, I do get 1. So number 10 is a probability distribution. 0 plus 1 sixth plus 2 sixths plus 3 sixths is 1 or 100%. Number 11 is what we would call a probability distribution histogram, or maybe even a relative frequency histogram. My values of x are the number of girls in 2 births. That's on the x-axis. They are numerical and they correspond to probabilities. So 0 has a probability of 0.25, 1 has a probability of 0.5, 2 has a probability of 0.25. Well, none of those bars are above 1, and none of them are below 0. And if I add up 0.25, 0.5, and 0.25, I do get 1 or 100%. So both 10 and 11, though they are represented in a different way, are probability distributions. We can use probability distributions to find a myriad of probabilities. For example, here's the example again with the number of 4 children with a genetic disorder. If I were to find the probability that out of those 4 children, exactly 2 of them have this genetic disorder, I would go to x, go to 2, and find that my probability is 0.3750. If I wanted the probability of all 4 out of 4 children having this disorder, then I would go to x equals 4 and get 0.0625 for the probability. If I wanted the probability that less than 2 have this disorder, well, that would be the probability that 1 or 0 have the disorder. So I could add those probabilities to get my answer. Probability that 3 or more have this disorder. I could add the probability of 3 to the probability of 4, and I would get my answer to that as well. There's a number of different things I can find using a probability distribution. Finding the mean, standard deviation, or variance of a probability distribution is a familiar process. Now, the formulas that are shown here are mostly new. However, the process itself is something that you've done before. I'll show you what I mean. For number 12 and 13, we'll find the mean, standard deviation, and variance of these probability distributions. So for number 12, we'll use the calculator. First thing I'll do using my calculator is, of course, turn it on and go to Stat. Just a second. I'm going to turn it on, go to Stat, and enter and into my list menu. And in list 1, I'll put my X values. In list 2, I'll put the probabilities that correspond to each X value. And to find the descriptive statistics I'm looking for, I now go to Stat, Calc, 1var Stats, and tell the calculator I'm using list 1 with a frequency list of list 2, either by using a comma if you have a calculator like this one, or by listing list 1 as the list and list 2 as the frequency list. That gives me my statistics, or at least 2 out of 3 of them. In this case, we use mu for probability distribution's mean, so mu is 1.5, and sigma, we'll round that, is 0.9. To find the variance, I'll either retype all of sigma and square it to avoid round-off error, or you can press vars, statistics, go to the sigma symbol, and square the symbol. The calculator will remember that that symbol corresponds to the number you just found. And when I do that, I get 0.75. To remain consistent, we'll round that to 1 decimal place. So sigma squared is approximately 0.8. Those are my descriptive statistics for that probability distribution. Let's repeat that process for number 13. Again, I'll find mu, sigma, and sigma squared, population variance. Well, we know that 1 squared is going to be 1, so the variance will be 1, but I'll repeat the process of using the calculator to avoid round-off error, and just in case you need to see it. Bars, stats, sigma squared, and sure enough, 1 times 1 is still 1. And I have my descriptive statistics. The expected value occasionally shows up in statistics problems. Expected value represents the mean value of the outcomes. It's denoted by E, but it uses the same formula as the mean. That's the exact same formula as finding the mean of a probability distribution. So for example, if I were going to find the probability or the expected number of girls in 2 births, then I would just find the mean of my probability distribution. Expected value is the same as the mean. They are the same. And I get 1. So, on average, I would expect for there to be 1 girl in every 2 births. That's the expected value. In the next video, we'll talk about a specific discrete probability distribution that's extremely special to us in this course. It's called the binomial distribution. It results from a procedure that has 4 characteristics.